Alright, so this video is a brief review of simple harmonic motion and graphing simple harmonic motion. The three situations we're dealing with when we're talking about simple harmonic motion are a pendulum, so string attached to some kind of mass swinging back and forth, a mass attached to a spring that's going back and forth horizontally, and a mass attached to a spring that is moving up and down. Okay, when we talk about graphing simple harmonic motion, we're always graphing from what's called the equilibrium point. And there's two important things about the equilibrium point. First of all, it's always in the middle, so the red dot is our equilibrium point. And second of all, it's where the total force in the direction of movement is equal to 0. Okay, so for a spring, we have equations for position, velocity, and acceleration, and they're pretty much the same for a pendulum, except that instead of talking about position as a function of time, we're talking about angle as a function of time. And all of these functions are going to look sinusoidal. And what that basically means is they move up and down. Okay, so let's say this is a position time graph. Okay, the time it takes to go through one whole cycle, so from one bottom to one bottom, or the top to one top, that is your period. That's how long it takes to go through one cycle and repeat itself over again. And then the height, and this is only true if you have a position graph, or in the case of a pendulum, a theta versus t graph. This is called your amplitude, and it's equal to your maximum change in position, or for a pendulum, your maximum angle. There are also some equations that relate the maximum velocity to the maximum position and the amplitude, as well as the maximum acceleration. Okay, so when we're graphing simple harmonic motion, the hard thing is always to find this guy right here. Okay, so this is called our phase constant, and it's pretty much the most confusing thing to find. Okay, before I tell you how to find it, I need to make sure that you understand what a sine function looks like and what a cosine function looks like. Okay, so from the last slide, you saw that position graphs should be something like cosine omega t. Okay, so a cosine function is going to look like this. It starts off at its maximum, and then it goes down and oscillates like that. Okay, negative cosine, so acceleration graph should be a negative cosine, is just the opposite. It starts out negative and goes positive. On the other hand, a sine function starts out at 0 and then goes up and down, etc. And what your velocity graph should look like if phi is equal to 0 is this last one. It's negative sine. So just kind of as a review, your x graph should look kind of like a cosine. Your acceleration graph should look kind of like a minus cosine, and your velocity graph should look like negative sine. Oops, that was sine. Should look like negative sine as long as phi is 0. So I should write that. Phi equals 0. Okay, but phi is not always going to be 0, because sometimes your cosine function, your position versus time graph might look like a sine function, or it might be slightly shifted over. And so to think about how to find phi, we have to go back to algebra. Okay, so let's think about the graph of x squared versus x plus 2 squared. Okay, they're going to look really similar, but because of this plus 2, you are going to have to shift the second graph over by 2, and because it's plus, you're shifting it 2 to the left. So x squared will look like this. Hopefully you should all know and love that by now. So that's x and y. And then x plus 2 is going to look like the same exact graph, but shifted 2 over to the left. And that should be -2 at the bottom. Okay, similarly, if you had cosine omega t versus cosine omega t plus 2, this guy is going to be shifted 2 to the left as well. But in order to find phi, you need to keep in mind that you're distributing the omega, so your angular frequency, both to the time and to this thing you're shifting over by. Okay, so in order to think about how to find phi, you need to think about the unit circle. So the unit circle is basically a different way of writing angles. So we're used to writing angles from 0 to 360. This is just writing angles from 0 to 2 pi. All right, so basically what you need to do is look at your function and see how far it is shifted over from where it quote-unquote should be, and then figure out what fraction of your period it is, and your phi is going to be that fraction of the unit circle. So for example, if your position graph looked like this, so say this is x and this is t, you should have a position graph that starts right here. So your graph is shifted over by this much, okay? And this right here is 1/4 of your period. So, and it's shifted over to the right, so you know you're going to be subtracting. And let's look at our unit circle. 1/4 of the unit circle is pi over 2. So if we were to write this one right here, it would be, you'd have cosine omega t minus pi over 2. Okay, so I'm going to do 2 examples. In our first one, we have an acceleration time graph. Okay, we know that an acceleration time graph should look like a equals minus a omega squared cosine omega t plus phi. Okay, so we want it to look like a negative cosine. If you go back to the slide where I had negative cosine, you know that it starts at its minimum value. Okay, so if we look at this, okay, we have the whole period is from 1 to 9. The whole period is 8 seconds. Okay, so the whole period is 8 seconds, and we are shifted over by 5 seconds. So our phi is going to be 5/8 of the unit circle, so 5/8 of 2 pi. Since we're shifted over to the right, okay, so since it shifted, this is shifted over, sorry, I'm at the choir concert, so sometimes it gets loud. This is shifted over by 5/8 of our period. Our phi is going to be 5/8 of 2 pi, which is 5 pi divided by 4. So, and since it's shifted to the right, we have omega t, and phi is negative 5 pi over 4. Okay, if you know the unit circle, you know that is also equal to 3 pi over 4. So phi equals negative 5 pi over 4, or phi is equal to
Where are they at?
3 pi over 4. Okay, so here's our second example, and this is going to be a position, so x t graph. Okay, we know that x of t should look like a cosine, because x is equal to a cosine omega t plus phi. So it should start at its maximum value, which is right here. Okay, if we look at this graph, we can see that an entire period, t is equal to 6 seconds, and this has been shifted over by 4.5 seconds. Okay, so once again, phi is just going to be equal to the fraction of our whole period that it's been shifted over. And so phi is equal to 4.5 divided by 6 times 2 pi, because that's the whole unit circle. And 4.5 divided by 6 is 3/4. So we have 3/4 2 pi, which is just equal to 3 pi divided by 2. Okay, once again, it's going to be negative 3 pi over 2 because it's shifted to the right, or if you know your unit circle, negative 3 pi over 2 is just equal to phi equals pi over 2.